Hi everybody. Today we're going to look at some more polymer chemistry. So some of the notes you see here were from class on Monday. This is here for your reference, but we're going to do the same thing for those of you who have class today on Wednesday. Since we have a little more time in lab today, we are going to go through this stuff. All right. So today I wanted to look at some of the waste issues around plastics and some of the environmental issues around plastics. I also wanted to look at which I think is here, yep, the practice sheet that I put up there for an assignment. So I'm going to go through all of these so that you have answers and you have kind of instructions for how to go through them, but don't watch it right now if you haven't tried these yet. So it's more useful if you go through the instructional material and then try to draw these on your own and then look at how I did them rather than just watch me do them. In fact, I would say it's almost dangerous from a learning standpoint. If you watch me go through these, it'll make sense to you and you'll go, oh yeah, I think I kind of get that. But then when it comes time to actually do it yourself, to test yourself, you still won't be able to do it, just like what a lot of you experienced at the midterm evaluation. So try it first, so you can really focus on just the parts that you need help with and then come back and look at these answers. I would also say if you haven't mastered the structure drawing from several weeks ago now, please get to work on that as well, because we will continue to use that through all of the rest of the material this semester. All right, so first, let's actually skip this for a second and take a look at recycling and waste issues, so you don't have to pause it and then come back. So you can follow along here, and then we will I'll tell you where to stop it when I start going through the problems again. Okay, so plastics, as we've talked about, polymer materials have lots and lots of advantages. They're lightweight, they're cheap to produce, they come from oil. Generally, although there are plastics that come from biological materials as well, like your bioplastics. They're often very water resistant. They're often very resistant to environmental stuff at all. So things like vinyl, polyvinyl chloride, which is used for example, for your perhaps for your siding for your house or your floors. Extremely weather resistant, basically will never break down in the environment, which is great for things like protecting houses. Not so great when those things become waste and can then sit in the ocean for literally thousands of years without any degradation. So how do we balance some of these issues around plastic? Well, I think the first thing to recognize is that all plastics are not, let's qualify this and say they are not fully recyclable, which surprises a lot of people. I think I mentioned this earlier at the beginning here. Yeah, that plastics are identified by this symbol, but this symbol, even though it looks like the recycling symbol, actually is just the symbol that the industry decided to use to label their plastics. It has nothing to do with whether or not that plastic is actually recyclable. And in fact, plastics are in general not recyclable. And what I mean when I say that is when we talk about what it means to recycle something, what it really means is you can make something out of this material and then you can reprocess it and make the same thing again. So example of things that are recyclable. Glass is recyclable. So you can take a glass bottle, you can melt it down, get some of the impurities out, and make a new glass bottle. Aluminum, like aluminum cans, recyclable. You can take aluminum cans, you can melt them down, you can make more aluminum stuff. You can, a lot of metal actually fits in this category. You know, you can take scrap metal again, you can melt it down, change its composition if needed, and make new metal stuff. So that's what we mean when we say something is recyclable. And that's what we should mean when we say something is recyclable. That we can take it and then make the same thing out of it, take it again, make the same thing out of it, and repeat this process forever. And that's what happens with things like glass and metal. But that doesn't happen with plastic. You can't take a plastic bottle, melt the plastic down, and make a new plastic bottle. It doesn't work like that. There's degradation in the material each time that you do that. And so, for example, the polyethylene terephthalate, which I don't have one in arm's reach right now, but basically the water bottles, the clear plastic water pop bottles that we see all the time, those are the most one of the most recyclable plastics in terms of having a market for them after they've been used, but they're not made into new bottles. They're made into other polyethylene terephthalate materials, such as fleece clothing, carpeting, things like that. And then eventually those materials get thrown out. In fact, in many cases, it's just a one-time reuse. So you recycle the plastic bottles, a fabric manufacturer buys the recycled plastic, makes it into a fabric, and then when you're done with that piece of clothing, it gets thrown away and ends up in a landfill. So it's maybe putting off the disposal of that plastic for a little while, but it's not really changing the fact that it's ending up in a landfill in the environment. Many other plastics do not even go that far. So, for example, polystyrene, which is both styrofoam and also, also things like these red Solo cups, polystyrene, even though they're not styrofoam. These are not recyclable at all. In fact, if those end up in recycling containers, they just get thrown away. So the way modern recycling works now, generally, is you put all your stuff in the recycling container, and it goes to a recycling processing center where the few valuable things are taken out of it. So aluminum cans, glass, probably some clear plastic water bottles, some paper if it's in nice shape, if it's like white paper that's in nice shape and not too damaged, maybe cardboard, and everything else is thrown away. So that's really how recycling works. Recycling is essentially a myth then that was really developed by the plastics industry in the 80s when they wanted to sell more plastics, and people were really starting to be concerned about all of this waste that was being generated by all of this increased use of plastics. So they kind of made up this idea that if we just tell people that plastic's recyclable and we make these recycling programs, then everybody will use more and more plastic and it won't be an issue because we'll just tell people it's recyclable and we'll just keep recycling it. And I don't know if that was purely cynical or if it was more like that they figured sometime down the line we'd come up with the right technology to actually be able to recycle things, but either way it didn't really work. But it did work from the standpoint of the plastics industry in that there's been a huge growth in the use of plastics for all kinds of things, from packaging, particularly single-use plastics, which are especially bad because they're generally just used once and then disposed of. And so now we have all this excess of plastic. So I think that we have to be a little bit careful with this issue. You know, how do we balance these two things? On the one hand, plastics are incredibly useful and allow us to do things that we would not be able to do without them because they're so light and strong. Even in high-tech applications, things like carbon fiber is really mostly plastic, even though it has carbon in it as well. Epoxies, other types of adhesives, a lot of even things like cars are held together by high-tech polymer adhesives that make you able to for example, fix different types of materials together like aluminum and steel, which you can't really weld. So there's lots of good things about plastics, but there's also this huge industry that's trying to grow and trying to get us to use as much plastic as possible. So I think the answer here is not to be pro or anti-plastic, but rather to think carefully about the times that we use plastic and when we can substitute more recyclable material. And then also just the kind of just lowering consumption in general. Do you really need to buy X new thing that's packaged in plastic, or can you do with something that already exists and doesn't need to be packaged? All right, so let's take a look. We'll talk more about this in the context of our bioplastics too after we do that analysis. So let's look at some of these structures. So for each of these first ones, I've asked you to draw a chain of some polymer units and then make the abbreviated form by looking at that. So the first couple are addition polymers, the second couple are condensation polymers, and then we have kind of a mix of some different ones down here where we're going the opposite way. We're looking at the overall structure and then wanting to break it down into the constituent parts. All right, so here we go. Okay. So we have this methyl methacrylate. This is our first one, right? Yeah. Okay. That's this structure here. This is a condensed structure. So we'll keep it in that form for now, and then we'll convert it to the line structure. Oh, by the way, pause your video now if you haven't tried these yet. Give them a try, and then come back. All right, so whenever we're looking at this type of a polymer structure, we first have to decide, is this going to be an addition polymer or a condensation polymer? This one we can see is likely going to be an addition polymer because we see the double bond there, and we don't see these like carboxylic acid or similar type groups that we generally associate with condensation reactions. So by seeing that prominent double bond, that's a good indication that that's where we're going to do our polymerization from. And so remember then when doing that, what we do is we kind of get rid of one of those bonds because those are the electrons that are used to do the connecting. And then we're going to connect the same molecule to itself over and over again on that side. So we'll keep everything the same. We're not adding or subtracting atoms here like we do with the condensation polymers. We're just rewriting the thing. And then putting another one right next to it. So instead of H2C, I'm going to call this CH2 because same thing. But if you said H2C, that's fine. Same thing here. And we'll keep going. All right, and that's about all I've got. Oh, I guess I have more room here. Do one more. This is always a good idea, by the way, to draw out a few units of the polymer before trying to kind of draw the overall structure or the abbreviated structure. So then we can look at this and we can say, all right, well, what's the repeat unit? What's the thing that keeps repeating over and over again? And it doesn't really matter where we start or where we draw it from. There's lots of different places. I'll just kind of pick a spot in the middle here and say, if I start about here and I go to there, that's like a repeat unit because that same thing is repeating over and over again in each other part. And so then to draw that repeat unit, I just redraw it down here. And then we always have these kind of lines that are coming out through the parentheses to show that it's repeating over and over again. And that's that repeat unit structure. Now this is still what I would call a condensed structure. So let's convert that to a line structure here next to it. So the line structures for addition polymers, the basic part inside the parentheses, it's always going to look the same. It's going to be like this. Because the reason for that is we always have these two carbons, 1, 2, that came from the two carbons of the original double bond. And then we just need to add the other things that are connected. So in this case, the two things that are connected are the CH3 and the CO2 CH3. I'm going to draw them both on the second carbon here. And because of the way we draw line structures, we draw both of those things coming off underneath rather than going up this way, which would cause a really small angle here. So it doesn't matter which one we put where. CH3, CO2, CH3. And then if we're really being strict about our line structures here, we could even remove that CH3 because we know that just that end of the line here means that there's a carbon there, and therefore there must also be 3 hydrogens on it. All right, so there's our repeating structure for methyl methacrylate, which is polymethyl methacrylate. This is the wrong name. I was wondering about that. This is not chloroprene. This is vinyl chloride. Chloroprene's a similar but slightly different molecule. Maybe that's what I meant to draw. I don't know. So this one is written in a sort of a hybrid condensed form / line structure. I'm going to add the CH2 here just to make it clear and so we have some consistency. We're going to do this in the same way. So once again, we rewrite the structure. And then we connect it multiple times without the double bond. So CH, Cl. Okay, and so on. So we're starting to see this repeating again. So I can once again find that repeat unit, which is like about there, let's say. Could also be over here, could also be over here, right? We have multiple choices here. Oops. But now we can write the structure like this. All right. Hopefully you got something. Oh no, I'm sorry. That's not right. I'm copying my former one. Let's try that again. There we go. That's what we should look at. And then we can convert that also to a line structure. So we'll have that same form, just like we did before with the 2 carbons. And now we just need to add the things that are connected. And in this case, the only thing that's connected is the Cl coming off the top there. So Cl. So there you go, polyvinyl chloride, aka PVC. Most things that we refer to as vinyl, except for the records, those are a different polymer, are made out of something like this. So like vinyl siding, vinyl flooring, vinyl, like the fake leather stuff. That's all made out of this or something similar. All right, so those are our addition polymers. Let's take a look then here at a condensation polymer. So this one's a little bit different from the examples above or the ones that we did in class in that it's just one molecule. But don't let that throw you off. We're still going to do the same thing. You just have to put that molecule next to itself and do the dehydration process or condensation process. So let's do that. In fact, just to save space here, no, never mind. I'll do it this way. So we're going to redraw this molecule. And then we'll draw another one right next to it. Okay, now to connect these, we want to do that condensation process. So just to more clearly visualize that, I'm going to break this NH2 out into an N here, an H here and an H here. Same thing, means the same thing. NH2 is NH2. We're going to show those so that we can show how these things combine. So we've got 2 H's and an O. That makes water. And if you're doing this with pencil or on a tablet or something, you can actually just directly erase this, can be helpful. So we're actually just getting rid of that, right? That's our water. Now, we want to know kind of in the back of our head, or we want to remember that that is actually water. It's not just nothing. But in terms of building the polymer, as long as we kind of know that there's some water floating around there, we don't always have to write it down. We care more about what that polymer would look like. All right, so that looks okay. I mean, that doesn't look great, but it is connected properly. So all we really need to do then is just take this one on the right, and move it over a little bit so it's a more consistent type of structure. So I'm going to get rid of this just so I can redo it here. Oop, no, I don't. Okay. So there's my N there. Okay, and so that's 2 units of the polymer. So if I want to do a third one, I just take that monomer molecule again and put it right next to the other one over here and connect them in the exact same way, and then do it again. And that would be 4. So maybe something that might be interesting is see if you can do this without drawing it. Once you've got a little practice, see if you can do it without drawing it next to itself and then doing the circles and stuff. So we can maybe just directly add this. You can even use the previous one as a template because you know it's going to be the same, right? So we can do this as many times as we want and just keep adding this thing together. So there's about 4. Okay, so then if we want to find that repeat unit, again, there's lots of places we can find it, but in a condensation polymer, because we know the polymer is made by this specific reaction, it's good to make that bond one side, either the left or the right, or actually both, of the polymer. So in this case, it's actually both. We can go here and here. Right? So we can say where we make that bond, that's where we're doing the repeating. So anything in between those newly made bonds is part of that repeat unit. And so then if we redraw it, we'd have something like this. All right. So then this one, I'm not going to draw this one out here because we did it earlier. So that actually is polyethylene terephthalate, which is up here. If you're watching from the Wednesday group, we'll be doing this in class today, or in lab today. All right, so then how do we go backwards? How do we look at monomers like these down here, or sorry, polymers like those down there, and break them apart to figure out the monomer they came from? Well, the first thing we have to do is, like we did before, we have to figure out, are these addition polymers that start with double bonds and then expand that way, or are these condensation polymers where we've removed water? And so the way you figure that out is you can hopefully see from these, you've got, in these first 3, these like just 2 carbons in those parentheses plus whatever's hanging off of it. So if you see that same kind of 2 carbon thing, that's addition polymers. Now, are there addition polymers of more than 2 carbons? Yes, but the ones that we're going to be dealing with, the majority of them, those work like that. So we can make that assumption for now. And then for 4 and 5, these have to be condensation polymers because we don't see that basic building block, that basic group here of 2 carbons. We see other things going on. We see double bonds to oxygen with more oxygen or nitrogen around. So those are all clues that we're dealing with condensation polymers. So let's look at a couple of the addition polymers first, and then we'll go down to the condensation polymers. Okay, so the first one here, I think this was an example from the last video. But you want to just do the reverse process of what we did before. So here we've got our 2 carbons, 1 and 2. And the lines coming off of them show them linking to themselves kind of over and over again with the double bond, or with the ring coming off. So we just need to reverse that and say, okay, well, let's get rid of those connections. And since we know it's an addition polymer, it starts with a double bond. So that's really the starting monomer. If we redraw that, it would just look like this. Notice we're not messing with this big ring or really anything else about the structure. We're just getting rid of those links and reforming that double bond between the 2 carbons. Right, so same thing here. Getting rid of the links, reforming the double bond between the 2 carbons, which I'm going to draw in a condensed form here just because otherwise it would just look like an equal sign. But it's just ethylene, and number 2 is polyethylene. okay, so then the third one, it says careful with this one. So what's careful about it? Well, it already has the double bond there. So this is not the same as number 2. Right? Those are different polymers, because number 2 is all singly bonded carbon, and number 3 is alternating single and double bonds of carbon. So those are different molecules. So they must come from a different monomer. They can't both be this one. And if you think about it a little bit, if you do the same process, get rid of those links, and then what's the other step of that process is adding that extra multiple bond. And so adding that extra multiple bond here would actually make it into a triple bond. So this one would be CH triple bond to CH. This is called polyacetylene because this molecule is acetylene. So very different polymer. Looks very similar, but if you keep that same process, you'd find the correct monomer there. All right, let's look onto these condensation polymers. So with condensation polymers, we have to break the bond that's formed in the condensation and then cap it, let's say, or put on the end H and OH. Because if we go back to what we did when we were building those polymers, I deleted it here, but we took H from one side, we took OH from the other side, we got rid of those, and we connected what's left. So if we want to make the monomer from the polymer, we have to do the opposite. We have to break the bond apart and then put H on one side and OH on the other side. So let's try that. Break the bonds, which would be here and here, and then cap it. Let's do the broken, so let's just redraw it with broken bonds and then figure out what we need to do to cap it. So we're just going to redraw everything else. Don't worry if it's big. And if you see that there's kind of another place you could break here, you're correct. We'll talk about that in a minute, but let's get this one first. You know what, I'm not going to have enough room there. Let me just do it over here. I'll just have to keep going back to look at it. Oh, light's turned off. All right, so I'm just not changing anything. I'm leaving this alone, except I'm getting rid of those connecting bonds from the two ends. Let me get the light back on here so I can see. Okay. So now the ends are going to have OH or H. Now which one is which is the next question. And the answer is, well, hopefully you've done enough of these now that you've seen that we don't really see structures that have OH coming off of an NH like that. Generally we see this carboxylic acid functionality. Whoops, you can't see that. This carboxylic acid functionality, the OH coming off of the carbon that's double bond to oxygen. And so that means that our H is on the other side. So we can leave it like that, or that is a monomer that would make that polymer. Nothing wrong with that. We can also simplify this a little bit and just say NH2 or H2N, because that's usually how we've seen these things. But if you're looking carefully, you'll notice there's another amide bond right here. And so this actually is one of those polymers that is made from two different monomers. So we could really do the same thing again and break right here. So we could go, here is one molecule, and here's another one. Because we know that these condensation molecules often do this. So we can then cap this with OH and this one with H. Again, it's probably a little cleaner to make that NH2. And those are the two molecules really that would make this polymer. This polymer, by the way, this polymer is what's known as Kevlar. It's a polyamide or a nylon. It's extremely, extremely strong and resistant to breakage because of all these strong alternating double bonds, these benzene rings. But those would be two molecules that we could break it down into. All right, number 5, polylactic acid. If you've ever done 3D printing, this is likely the plastic material that you've used for that. So again, we're going to do the same process. This time, it's pretty clear there's just one place to break it. But the thing that's a little bit confusing perhaps about this one is where are we going to do that? Where are we going to make that, that break? So let's draw out a couple of it just so we can see what that would look like. So what happens here is, actually I'm going to delete that one. So we could have the O going down here, and then that would connect to another one of these carbons right there. I'm going to flip the direction just to make it, just to keep the zigzag going. I keep hitting some button or something here, sorry. So this is what that polymer would look like if we keep going and keep going and keep going. So it's, again, this, oops. So in this case, that is not the bond that is breaking here. It's this one, right? It's the ester bond. So we end up kind of with like what looks like we would break it into two molecules, but it's not really two molecules because this is then connected to the front of this. So I think it makes more sense here to look at the structure and look at where this thing was breaking on both sides. So really, that's a better way to draw this. And really, it would make more sense to use that as a repeat unit rather than what was used here, so that it's more obvious. But, you know, people draw structures how they draw structures. If you found this one, you still have to know what it's made out of. So if we break it this way, it becomes a little bit more obvious. That we need to add the OH here and the H on the O over there. And so that's the monomer lactic acid. That was a tricky one because of the way it was drawn. We couldn't just say, oh, we'll just cut it at the ends like we could with this one and put H and OH. With this one, we really had to look at the whole structure first so that we could break it at the appropriate positions. All right. So give those a try, give those some practice. I think there's a little bit more in the linked textbook chapter, but hopefully by the time you get through these, you have a little more comfort with drawing these structures. If you still need more practice, look up anything about common polymer structures and look for the monomers and look for the polymers and see how they go together and test yourself and say, okay, this is the monomer. A good way of checking this is every monomer and polymer have the same name. Well, not every. A lot of them have the same name except for the word poly. So if you're looking at a polymer called polytetrafluoroethylene, which is Teflon, you could look up that structure and then you could try to draw the structure of the monomer tetrafluoroethylene to test yourself out. You could also say, okay, I know there's polypropylene, so I'm going to look up a structure for propylene and then see how I would polymerize that. And then you can check those as well. So lots of options, and of course, always come see me, come ask if you have more questions or you want more than that. All right, hopefully this goes okay, and I will see you in class. Bye.